Okay, hi Will and hi Austin. We hope you are well wherever you are. We're going to be talking today about rotational kinetic energy, the energy that an object has because it is rotating about a point. And we're going to fairly quickly develop a formula for rotational kinetic energy, but the trick is going to be to visualize it correctly when you look at an object's motion. So I want to begin by considering just a bar that is rotating about its center of mass, C, right here, with a speed omega. Now first, it is clear that the bar has kinetic energy because of its rotation, for the simple reason that if you take that rotating bar and you put it in contact with something else, maybe a ball or something like that, then it will impart kinetic energy to that ball. So it's clear that the object, the bar here, has kinetic energy. But we wonder how much. And so to find out how much, we're going to do a classic calculus move. We're going to divide up the bar into lots of little pieces dm. We're going to compute the kinetic energy for each piece dm and add up. So let's take a representative piece dm right here. And because dm is moving, is rotating about to the center C, it has a speed to it. And at any given instant, its velocity vector is going to be tangential to its motion. So the motion dm is going to be in a circle, so. And so we can say that the kinetic energy contributed by dm, which we're going to call dk, one small unit of energy, is equal to 1/2 times dm times v squared, where v is the speed of that particular dm. Now, this is useful and we can integrate it, and in fact, if we did integrate it over all dm's, then we would get that k equals the integral of 1/2 dm v squared, which is going to give us, then ultimately, summing up all the kinetic energy of the pieces. So that's easy, but it's also not very helpful because it doesn't relate it to the rotational speed omega. And because each one of these velocities, speeds, are going to be different for each dm. In particular, the dm that sits right at the center is not going to be moving at all. And the dm that is going to be out at the edge is going to be moving much faster than the dm that will be moving twice as fast as the dm that's halfway to the edge. So we're going to replace the speed v . We're going to replace the speed v with the familiar expression v equals r times omega. So that what we get is r omega squared rather than v squared. And now if I simplify a little bit, and also write the dm over here, then I get this expression for the kinetic energy, which is a nice expression, but it doesn't convey a lot of insight. What it's saying is that the kinetic energy is going to be the sum over all of the pieces of mass of 1/2 times the radius of that mass squared times the angular speed of the object, omega squared. I observe that 1/2 and the omega square are both constants for this object. Now, what do I mean when I say that omega is constant for this object? What I mean is that all of these points that are moving on the bar right here all have the same omega because they're under rotation. And so the omega does not depend upon which particular dm I pick. It's going to be the same for all dm's. And so it is a constant and can come to the outside of the integral. And when we do, we are left with a really familiar looking integral. What is that thing? Big red. It is the moment of inertia of the object, in this case, center. And so we end up with a very elegant expression for kinetic rotational energy. And I'm going to capture it in this formula here, just giving it its own symbol. K rot, or rotational kinetic energy, is equal to 1/2 times I omega squared. Now, what I'd like to do is to do just a quick example so we can get some numbers on the table, because then I want to talk about visualizing what's going on. But just to emphasize, what this formula does is it captures all of the individual kinetic energy contributions of all of the atoms in this bar. It takes all of those kinetic energy contributions and adds them together to give you the total kinetic energy of that bar as it rotates that center. Okay. Now, let's do an example. Find the kinetic energy of a disk of mass 1 kilogram, radius 0.25 meters, spinning about its center. One thing that I want you to observe about this question is that it does not explicitly specify whether we're talking about kinetic energy or, rotational kinetic energy or translational kinetic energy. So we as the problem solver actually have an option as to whether we want to compute that kinetic energy through 1/2 mv squared or through 1/2 omega squared. And here, the choice is really clear because we are looking at this disk spinning about its center. I didn't give you a rotational speed. Here we go. There we go. It's speeding 2 radians per second. So because our object is spinning about its center, it makes a whole lot of sense to consider all of the motion to be about that center. And I can easily compute the I for that center because we already have a pre-packaged formula for it. I is equal to 1/2 mv squared, taking our solid disk formula. Let's see, 1/4 squared, 1/32, whatever that is. Okay, so 0.0325. And therefore, and that's I about the center, and therefore, we can say that the kinetic energy is equal to 1/2 I omega squared might have been 0.0312. Let's see here. 2.0625. Yes. So this is 0.0625 joules, just like that. Now the thing that I wanted to stress here is that the kinetic energy was entirely captured by rotation because this center, C, is not moving itself. The center is staying put. But if we were to change this problem and to include some motion of the center, we would have to now consider both the rotation of the object about its center and separately the movement of its center together with it. And we would have to combine those two energies. And the reason that we do that is that if my object is moving, if the center of my object is moving, as all of these points are rotating, then if I consider the motion of a point P, that the motion of that point P is going to be kind of a spirally sort of motion, like this, as it goes about the center that is moving. And it turns out, if you think about this, it makes sense, that if you take any motion in the plane, you can describe that motion as a combination of translation and rotation. Any motion is in the plane is a combination of translation and rotation. And so this means that the total kinetic energy of an object is going to be the sum of the kinetic energy because of translation and the kinetic energy because of rotation. That is, it will be 1/2 mv squared, where v is the motion of the point of rotation, or the center of rotation, combined with 1/2 pi omega squared. And if you want to think of this formula as the one that summarizes what we do, it's really this. And to use it well, all we have to do is to identify the appropriate point of rotation. So let's revisit our disk and let's add to its motion. This is 1 kilogram, mass 1 kilogram, and radius 0.25 meters. Is moving to the right at 3 meters per second. It is also rotating at a rate of 12 radians per second. Find its kinetic energy. So notice that this problem takes our previous problem and it now adds to it translation. So we can say that our big formula for the day, total kinetic energy equals translational plus rotation. And we now consider what is happening. First of all, to the center. It is moving to the right at 3 meters per second. And then additionally, points on that disk are going around at 12 radians per second. So that we can now plug in we had previously computed the moment of inertia I. As 0.0315. Now before we give the final answer, I want to examine each of those terms separately. When I compute the first term, I get 4.5 joules. When I compute the second term, I get 2.25 joules. And what I'd like to observe is that these two terms are comparable in magnitude. They're not the same value, obviously. This one's half of that one. But my point is that both of them are adding appreciably to the kinetic energy of the object. So if you go back and think of all of the energy problems that we worked back in Chapter 7, Chapter 8, basically what we were doing was ignoring rotation because the objects that we were considering were not rotating, or they had a negligible radius, so that their rotational component of kinetic energy was zero. So we've actually been using this formula here all year long. We just had negligible components of rotation. That's all. So, practical application of this is what happens when you play ping pong. You guys play ping pong? Yeah. Okay. When you play ping pong, one of the great things that you can do is to impart spin to the ball. And particularly you can impart topspin. Topspin is awesome. Because when you impart topspin on the ball, what happens is that the ball appears to be moving at one speed, and then it hits the table when it bounces off. It's surprise, moving at a different speed. So it appears to be a kind of magic. It isn't magic. What it is a transfer of rotational kinetic energy into translational kinetic energy through the frictional force between the ball and the table. So here comes my ping pong ball, and it has an angular speed omega, and it's got a translational speed v. And now that ball hits on the table right here and experiences a frictional force that is going to oppose its rotation. Well, that frictional force that opposes its rotation must necessarily point in this direction. And because it is pointing in this direction, it is going to increase the speed of the ball because it's pointing in the same direction as the velocity vector. So you have this force that is pointing not in exactly the same direction, but the cosine of the angle between is going to be positive. And so for that reason, it does positive work on the ball. And the result is that v prime is greater than v. That's it. Now, I want to consider a scenario that can be analyzed in two different ways, and it is what we would consider to be a classic problem. suppose I have a ball, and for sake of definiteness, we give this bar a length of L and a mass of M, and we're going to pin the bar at the left end so that it is free to rotate without friction. Now we're going to raise the right end of the bar so that it is at an initial angle of 45 degrees. Let's just make it an initial angle of theta. We're being gentle about it. And we're going to release it. This is not a hard thing to replicate. All you need is a meter stick right here, and if you'll apologize for me not having a frictionless pivot to work with, that's exactly what we're doing. So the question now is going to be, how fast is the tip of that bar moving, point P, when the bar hits the ground? So, we can analyze this situation in two different ways. We can analyze it either by considering motion around the center of mass, or by considering motion around the pivot O. And it is my contention that it's easier to analyze it around point O. So let's do that at this time. If we analyze it around point O, then we can analyze it in terms of energy transfer. We are going to be converting potential energy for the object into kinetic energy for the object. And so our basic form here is that delta U equals negative delta K, conservation energy. Now, a change in potential energy is going to be the change of the motion of center of mass of the object. In other words, gravity is going to pull down straight through that center of mass. And as a result, the whole thing is going to fall a distance. Well, what distance? Well, this side of the rod right here is L over 2. And it forms a nice little right triangle right there with the opposite side theta. So therefore, this is L over 2 times sine of the initial angle theta. And so my center of mass drops by that amount. And so my kinetic energy, my potential energy, goes from mgl over 2 sine theta down to 0. Meanwhile, over here on the right-hand side, I need to consider how I want to express my kinetic energy. And if I choose point O as my pivot point right here, then point O is not moving at all. It is not translating. And because point O is not translating, therefore, I can consider all of the kinetic energy to be purely rotation about point O. So that seems like a good bet. Because I can now express this in terms of 1/2 I about O omega squared. But this is relatively easy because this is a long thin rod. The moment of inertia about the end is 1/3 L squared. So that I get mg L over 2 sine theta, multiply both sides by -1, equals 1/2 times 1/3 L squared omega squared. And if we do a little bit of canceling in the factors, we have a factor of 1/2 that can cancel. We have a single factor of L that can cancel. We have a factor of M that can cancel. It does occur to me that we might want that factor of L back. That's one way to think about it. But if I simplify what I've got L omega squared equals 3g sine theta. Now the question is, how do I relate this information to the speed of point P? And so to answer that question, I need to consider the speed of point P in terms of its rotation about O. And the radius of point P is all of L. Therefore, I can write omega right here, the rotational speed, as the speed of point P divided by the radius. And I can replace omega with speed over radius. Very, very common method here. And you can see that if I had left my factor of L on the right-hand side without canceling it, then I would have been able to cancel both factors of L when I simplify. As it is, I'm going to end up having multiple. So that V squared is equal to 3GL sine theta, or V is equal to root 3GL sine theta. Okay, now I want to observe a couple of things about this result. First of all, observe that this result is greater than the result we would have gotten if point P were just a ball dropped from a height of L sine theta. Point P starts at L sine theta, but because it is being dragged along by the entire rod, point P is actually moving much faster, well, by a factor of 3 over 2. So not much faster, but somewhat faster than just an object would be in rotation. So that's the first thing I want to observe. Second of all, our choice of point of analysis, point O, which was driven by the fact that point O is not moving, was superior to choosing point C, because if I had chosen point C, I would have had to consider the translational speed of point C in addition to the rotation of P about point C. And that's a much messier computation. So the moral of the story is, if you can choose a stationary point of rotation, if you can find one problem, then you can treat the entire thing as purely rotational. We have a few minutes, so I'd like to actually extend this to what we're going to be talking about tomorrow, which is rolling motion.
Like bowling?
It could be a bowling ball, sure. Let's start with bowling ball.
Good job, Danielle.
Now let's see here. I got to guess a little bit. So a 10-pound bowling ball is going to have a mass of about 4.5 kilograms, and it's going to have a radius of, let's call that 10 centimeters. I'm guessing on that. If anybody wants to correct me with the intervals, feel free to do so. Let's just make it easy to make mass in and radius off. Now, this is one of the biggest lies in the history of physics classes. Bowling balls do not roll without slipping. They actually do slip and skid a fair amount, especially if you roll them hard. You guys bowl at all? So you know what I'm talking about. You know, if you really wind up and let it go, that bowling ball is gonna skid a fair amount. So we're here really talking about a child doing a granny shot down the middle, so that this thing rolls without slipping with a speed of v. Find the kinetic energy of the ball. Now, the reason that rolling without slipping is going to be important to this problem is that rolling without slipping is going to force the angular speed and the translational speed to be linked together. Rolling without slipping compels the angular speed and the rotational speed to be related to each other by the expression omega equals v over r, or v equals r omega. Now, why is this? Well, consider this bowling ball as it rolls down the lane with a speed of v. In order for it to roll with the speed of v, what has to happen is that the ball must roll about this point of rotation right here. We talked about that previously. And once the ball has gone a distance of 2 pi r, its center has gone a distance of 2 pi r, then it will have rolled about the center a distance of 2 pi r as well. In other words, it will have undergone one rotation. So what this means is that all of the points on the edge are going to have a speed of v relative to the center of mass. Relative to the center of mass. Not relative to the lane that it's rolling. Remember that we talked about how this guy right here is motionless, and the one at the top has a speed of 2v relative to the lane, and this guy right here has a velocity vector that is going to be v in the I direction and v in the j direction, right? So that's relative to the lane. But all the points here are going to have a speed relative to the center of v, which means that their speed is equal to r times omega. In other words, omega must be v over r. If the ball rolls with slipping, then omega will necessarily be less than v over r. Well, if you have like a motorized ball that can somehow be spinning about an axle, then it could actually be greater than. But balls that are rolling with the slippage are going to have speeds that exceed our omega threshold. Now, that means, since we're rolling without slipping, omega equals V over R, then I can say that the total kinetic energy is equal to K trans plus K rho, or 1/2 mv squared plus 1/2 times omega squared. And now when I go substituting in the second term, first of all, I look up the moment of inertia of a solid sphere and find that it is 2/5 mr squared. And then I replace omega with what it is, which is V over R squared. And something really interesting happens. And that is that the R squareds cancel out. And as a result, I'm left with two different terms, each of which express the various contributions to the kinetic energy. I get 1/2 mv squared, contribution from the translation, and I get an additional 1/5 mv squared as contribution from the rotation. So that when the dust settles, the total kinetic energy that my ball has is greater than 1/2 mv squared. It is 7/10 of mv squared. And I can express it in terms of the speed, m is the mass of the speed, because v is linked to v. So tomorrow we're going to do this and also roll wheels and so on and so forth. We're going to use that to analyze the speed of objects as they roll down planes. And we're going to make some predictions about which objects roll the fastest. Fair enough?
The radius doesn't matter. That's all.
Taking a look at the formula, what would you say? Yes.
So, and then you said which one to roll the fastest. Wouldn't that just depend on the dust?
But it might. Well, let's see tomorrow. All right. I'll see you tomorrow.